Today we're looking at another kind of transformation. This one is called a dilation. You've learned about this one before. It's where we take a shape and make it bigger or smaller. So we're going to review the things you already know about dilations and add a few new ideas to what you already know. So starting out, dilations can either enlarge or reduce a shape. So we can take an original shape and make it grow or shrink. So I can take this triangle and I can scale it up to make it the same general shape but a bigger version. So before we dealt with congruence transformations. In this case we're going to be dealing with similar figures. So rather than congruent shapes, we end up with similar shapes because we're scaling this shape up proportionally. That means that we are making it, in this case, say 2 times as big in both the x and the y direction, so that it grows what we call proportionally. So we end up with a similar shape. Similar shape means all angles are congruent and all side lengths are proportional. So if I divide one side length over its corresponding side length in the new shape, I'll get the same ratio for every pair of sides. So all that should be review. You should know about similar shapes, about enlarging and reducing. So some new things. Oh, you should also know about scale factor. Scale factor is something you learned about before, where the amount that we scale up or down we call k. So if I take a shape and I make it 1/3 the size, then we say k equals 1/3. So that scale factor k is the ratio or the proportion that those sides have. So we said all the sides were proportional, and that k value tells us what we would multiply the original shape by to get this corresponding side of the new shape. So here we would multiply this length by 2. Here we would multiply our radius of the circle by 1/3 in order to change that shape. So k, the original shape, times k gives us the new shape. So again, all old stuff. So something new we're going to look at is when you did dilations before, your center of dilation was always at the origin. So we want to look at cases where it's not at the origin. So we need to make sure we understand a little more than just the rule that you learned before, which is xy becomes kx and ky. So that is applicable if our center of dilation is at the origin and we're dilating on the coordinate plane. But we want to extend our thinking and now be able to dilate a figure about any point. So if I took a square here, and this is going to be terribly not to scale because of how I'm drawing here, but if my center of dilation is the origin, and I want to double the size of this, so I want to have a k equal to 2, what I would do is take my distance to each point, so say this corner was at -1, 1, I would double that and let's actually do a k of 4, make it 4 times as big. I would go to -4, 4, so like right here, and I would make my, if this is A, I would make my A prime point right here at -4, 4. So I'm applying this rule here, just multiplying k times the x and y coordinates. So then I would do the same thing for B, C, and D, if those are those points. But what I want to look at here is the idea that we are taking the center of dilation, and if we draw a line segment out to a given point, then to find its dilated spot, we're going to keep following that same line of action. So again, here it's not drawn very well, but I should be able to draw a straight line from the origin through A all the way to A prime. And my ratio should, this k equals 4, should mean that from the center of dilation to A prime is 4 times the length of the center of dilation to A. So with that idea, my center of dilation doesn't have to be at the origin. It can be anywhere. I could take a square over here and put my center of dilation down here, and all I need to do is make sure that my k value tells me the ratio of the distance from here to here and then here to wherever the new version of that point is. So the distance from the center of dilation to the original pre-image point and the image point, that ratio is k. So we'll do some examples of this with the center of dilation at a different spot so that you can see exactly how that works on a coordinate plane. But that is one of the main new things we want to add here, is the idea that it's not just kx, ky. We can expand our use of dilations to put our center of dilation, pre-image, and image basically anywhere we want to. So our other concept, which you have learned before as well, it's usually a struggle when we learn this one, is called change in dimensions. So change in dimensions has to do with how k affects area and volume. So if I have a square, and it's 2 inches on each side, if I apply a k value of 2, let's do 3, I always use 2. A k value of 3, my new square will be bigger and will have side lengths of 6. I multiply each of those side lengths times 3 to get my new ones. So this is a linear value, right? So this line of 2 gets scaled up to a line of 6 by multiplying by 3. But the change in area is much greater. So I can fit more than 3 of this square into my new bigger square. The way we figure that out, so the area here would be length times width is 4. Here, length times width is 36. So if I drew this better, you could see that I could fit 9 of these squares into this square. So it didn't scale up by the k value, it scaled up by the k squared. Because what happens is we scale up the length and the width of the shape, or the x and y dimension of the shape. If it's not a square or a rectangle, it can be any kind of shape. But we scale up the length and the width of the shape both by k. So the area, which is length times width for a rectangle or something similar for other shapes, we're multiplying those 2 dimensions together, we end up with multiplying both of those by k. So we get KL times KW. So if we group the k's together, that would be k squared LW. So our relationship between the original area and the new one, we need a k squared in there to take care of it. So even if we don't have the side lengths, we know that the ratio or the effect on the area is always going to be the square of k, not just k itself. Volume works similarly, but then we're going all the way to 3 dimensions. So if I have, say, a cube, and I scale it up, so say this cube again is 2 per side, and I'm going to double it, so k equals 2. Then I'd end up with a cube that is bigger, and each side of this one, that's a terrible cube. Okay, each side of this one is going to be 4. So I have a length, a width, so I would say a width, a height, and a depth here, the way I drew it, of 4. So my volume here, 2 by 2 by 2, would be 8. My volume here, 4 times 4 times 4, is going to be 64. So I can fit 8 of these cubes into this cube. The idea there is that we doubled every side, or applied k times to every side. So I went from having length times width times height, however you want to say that, to having k times the length times k times the width times k times the height. So that k value shows up 3 times because it hits all 3 dimensions. It hits my length, my width, and my height. So if I group those together again, I end up with k cubed, k times k times k, times the length, width, and height. So my relationship between the original and the new one is that I need to apply k cubed to that volume in order to account for the fact that I scaled all the sides up by 2. So that's just a tough one to remember for some people, but we got to remember that This k is a one-dimensional value, so it affects lengths, but area and volume are 2D and 3D values. So in order to make the k apply to them, we're going to have to apply it multiple times in multiplication. So when we multiply by it twice, we get k squared. When we multiply by it 3 times, we get k cubed to modify the area and volume. Okay, so let's take a look at some example problems for dilations. We've got our first one, a trapezoid EFGH. We're at negative 8, 1, 2, 3, 4, 5, 6, 7, 8, and then 4, 1, 2, 3, 4. So I've got point E right here. F, negative 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. F is going to be up here. G is at 8, 4, so that's the same height as E, 1, 2, 3, 4, 5, 6, 7, 8, and then the same height as E right here, G, and then negative 4, negative 8 for H, so that'll be 4 left like that one, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got our original lines. I'm going to do my best to connect these. As usual, it won't look very good drawing on the computer, but I will try to get the rough idea of connecting the lines here. It looks like we have a trapezoid type shape. Oh yeah, trapezoid, there we go. So we're going to graph the image after a dilation centered at the origin. So that means we just need to multiply our coordinates by our k value, and k equals 1/4. So we're going to take xy, and we're going to turn that into 1/4 x, 1/4 y. So basically divide all of our coordinates by 4. So instead of negative 8, 4, E is going to be at negative 2, 1. Right here will be E prime. F is going to be, instead of negative 4, 8, is going to be at negative 1, 2. So that's F prime. G, instead of 8, 4, will be 2, 1, right here. And H will be negative 1, negative 2, right here. Okay, so we have our new shape, and it's important to check that it looks like a similar figure. So it looks like we have basically the same shape but scaled down, so that's good. Something else I want to look at, it's going to be, again, difficult since I can't draw straight, but if I take a line from my center of dilation and draw through G and keep going, I should run into G prime at 4 times as far away. So we haven't talked about how to measure distance on a coordinate plane yet, but remember the Pythagorean Theorem. We can think of the distance here as being the hypotenuse of this right triangle, and the distance to G being the hypotenuse of this right triangle. So if we checked those two, the hypotenuse of the bigger triangle would be 4 times as big as the hypotenuse of the small one. And I should always be able to draw a line of action from my center of dilation out radially, and it should pass through both the pre-image and image along the same line. So, kind of like that. Terrible, terrible. Okay, but you get the idea. So that's how we draw a dilation with the center at the origin, but now let's look at something new where we're going to do a dilation, but the center of dilation is going to be at a point on the coordinate plane that's not the origin. So this time, we're going to start off with triangle ABC. We have negative 2, 1, 2, 3, negative 4. Right here is going to be A. B is at 3, 2. And C is at 0, 4. 1, 2, 3, 4. So we'll do our best to connect those. Okay, something like that. And we want to do a dilation centered at 1, 2. So our center of dilation is moving. It's not the origin, it's this point right here. So we're centering our dilation about that point. And to find our new points on a coordinate plane, we can just basically make a line to the point and then follow that line further. So that line was 1 left and 2 up, again thinking about right triangles. So that left and up distance determines the diagonal, the hypotenuse. So we can make a similar triangle that's 1.5 times as big, and that will give us our new coordinate for C prime. So instead of going 1 left, we're going to go 1.5 left right here. And instead of going 2 up, we'll multiply that by 1.5 and we'll go up 3. 1, 2, 3. So C prime lives right here, 1.5 times the distance from that point right there. So B was exactly 2 to the right of our center of dilation. So instead of 2 to the right, we're going to go 3 to the right, and B prime will be right here. Then for A, we needed to go left 1, 2, 3, and down 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6. 6. So to go 1.5 as far this way, 3 becomes 4.5. So we're living between these two lines. And instead of going down 6 units, 1.5 times that would be 9. So we'll go down 1, 2, 3, 4, 5, 6, 7, 8, 9 units, and we'll drop our A prime point right here. So if we connect A, B, C, we should end up with a similar triangle to the one we started with, but you'll notice that they're not centered around the origin, they're centered around this point right here. So we would draw our lines of action from that center of dilation, and it would pass through A and A prime, or B and B prime, or C and C prime. So that's how we can do a dilation on the coordinate plane that's not using the origin as the center point of dilation. We're just going to make similar triangles and go apply the k value to the horizontal and vertical distance between our 2 points. So hopefully that makes sense. That's our new thing with this, is the idea that we can move that center point. There's one more example problem here. I'm going to go ahead and skip over that one because we already have kind of seen the examples of how these problems work. If you'd like, you can pause and work on this one. And then these are our problems to work on from the book. They're posted on Canvas as usual.